Section 2.3, Discrete Fourier Transform. In spectral analysis of audio data, our goal is to determine the frequency content of a signal. For analog signals, we use Fourier Transform. For digital signals, we use Discrete Fourier Transform. We'll begin with the definition of a Fourier transform. For a function x of t, a continuous signal in the time domain, the Fourier transform is defined as in this equation. X of t, the signal, times e to the minus I omega t is integrated over minus infinity to infinity about time. And here, omega, the angular frequency is 2 pi f. F is the frequency. For each chosen omega, this integration will make a complex number. These values are available for all omega values. Then from the collection of capital X omega, we can recover the original signal in the time domain. That is about the inverse Fourier transform defined as in this equation. Here, the capital X omega times e to the I omega t is integrated over minus infinity to infinity about omega and scaled by 1 over 2 pi. You can see a similarity between these two equations. Now, the integral is about t, and that integral is about omega. And now we have here negative sign, but here there is no negative sign. And also we have here scaling factor. Okay. This identity, e to the I theta equal cosine theta plus I sine theta for real value theta, is called the Euler Identity. We'll consider details of this identity in chapter 3, and we'll try to derive it, and we'll also consider applications of this identity. Okay. Okay, now we go to discrete Fourier transform. In reality, most of the signal is in digital format. So here, this is a discrete signal. Now, x and delta t. And delta t is a time interval between the signal, the points, so that x and delta t is nth value in signal. All collection is a discrete signal. For the signal, the discrete Fourier transform is defined as in this equation. Now the signal, and now e to the minus I, 2 pi, okay, k delta f. Delta f is the frequency interval, frequency increment, and 2 pi frequency is like omega, and n delta t is discrete function of time t. Okay, that is summed over 0 to n minus 1, assuming we have n discrete data points. And output is also n, capital N values. Each one is a complex number. And here we'll see details of the notations. Capital N is the total number of discrete data points, and capital T is the total sampling time. And so here delta T is time between data points, must be capital T over N. Delta F is the frequency increment, or sometimes called frequency resolution, must be 1 over capital T in hertz. F sub s is the sampling frequency per second, so it must be 1 over delta T, and that is now capital N over capital T. And this portion in computation, this portion will be used again and again. So once we try to simplify by saying over there the identities, then K delta F times N delta T must be Kn over capital N. Okay. Now, you can see the similarity from this formula with the continuous Fourier transform. Here, look at again. This is a time domain signal, and e to the minus I omega t, and integration is over t. So here, the summation is over, n is moving from 0 to n minus 1, so the summation is in time direction, and there's an e to the, it's an analog of e to the minus I omega t. Okay? And also this is x of t and summation, so that it make a complex value in the transform domain, frequency domain. Okay. Now, similarly, once for every k is from 0 to n minus 1, this frequency domain value is available, then now we can recover the original discrete signal. So that is the inverse discrete Fourier transform. And here you can see quite easily the similarity. Now the summation is over frequency, and that is frequency domain complex values, and e to the I, okay, this is about omega, this is about t, and there's no negative sign, and scaling factor is now 1 over n rather than 1 over 2 pi. Okay. If you are working on discrete Fourier transform, then you'll meet the phrase fast Fourier transform. The fast Fourier transform is simply a discrete Fourier transform that is faster. To get the value fast, and algorithmically it is manipulated. However, the result must be the same as discrete Fourier transform, so that all the rules and details about discrete Fourier transforms apply to fast Fourier transforms as well. Here we have some restriction for some FFTs, the power of 2 restriction. Many Fourier transform, fast Fourier transforms, for example, the one in Microsoft Excel, restrict n to be a power of 2, such as 64, 128, and 255, and so on. The FFT in MathTalent has no such restriction. Okay? So that we'll not go to the detail about the fast Fourier transform. That is on just the fast version of discrete Fourier transform. Okay. In this example, we'll try to generate a synthetic signal for time is 4, so during the 4 seconds, and at a sampling rate 100 hertz. That means that for each second, 100 points will be made, and during the 4 seconds. Then compute as DFT and restore the original signal by applying the inverse discrete Fourier transform. Here, let's begin with the discrete Fourier transform and its inverse. Okay. Now, for discrete Fourier.m, we define discrete Fourier transform. And here, now we count the length and we initialize to be 0 for the output in the Fourier domain, frequency domain. And we already know that the quantity is the same as Kn over capital N. So here we used that one here, Kn over N, and so that minus I 2 pi Kn over capital N. That is now multiplied with the time domain signal. Okay, in MathTalent, the index starts from 0, from 1, so that we are using n plus 1. Now, this loop is over all frequencies from 0 to n minus 1. Now, the inner loop is loop over all time domain samples from 0 to n minus 1. However, the earlier in MathTalent, and index starts from 1, so that's the reason we are using here n plus 1, k plus 1. Yeah. So for each k, here we from 0 in the beginning, now we add these quantities for all n, so that we get eventually this one will have the dot product of this signal n, the corresponding vector from here. Okay. Okay. Now discrete Fourier inverse is now doing the inverse discrete Fourier transform. Okay, the same, but now we are using small x, capital X. However, this small x will be the frequency domain signal, and the capital X will be the output, so that it must be time domain signal here. Now, inner loop must be over frequencies, and outer loop for each time we compute this one, and then we go through all the time. And here the formula doesn't involve here negative sign, and okay, so that the output is making here now that quantity for each n, and then at the end we multiply 1 over n, the scaling. Okay. Now first we implement that discrete Fourier transform and inverse discrete transform, and then we'll use them to solve the problem. Okay. We'll try to generate a synthetic signal, and we combine two sinusoidals, and one has frequency 10, the other one has frequency 20, and also magnitudes are 1 and 2, as in this line, sine 2 pi 10t, so its frequency is 10. Now for that one, 2 pi 20t, and frequency is 20, and magnitude is 1, magnitude 2, and combine them. And of course over there, capital T is 4. Now the sampling frequency is 100, then time vector must be given in this way. So we can make a plot and here save it. Now by using discrete Fourier transform, we get frequency domain values, and from that here the magnitude square can be computed, and also phase can be computed. The phase means that angle of the value, and measured from, if you here identify the complex value in complex domain, then you can measure the angle from positive x-axis to the point. So that is the phase by using arctangent 2 function you can get the angle components. Okay. Now, and from capital X, that is signal in frequency domain, by using discrete Fourier inverse, we can restore in time domain the signal. So we try to measure the distance between original signal and restore the signal. Okay. Now the result of that one is that one, so that except the rounding error, it is well restored. Okay. Here, now here we try to, okay, for the purpose of figuring, we make the frequency vector and we make the plot for the magnitude and plot for the phase and save the in image along with a subplot format. So that'll be on the top and that'll be on the bottom, and so that we have two images out of this program. That is the signal. It is combined. One is frequency 10, the other one is frequency 20. Now this is magnitude spectrum. Here we see clearly frequency 10 magnitude, and then at the frequency 20, and again 80 and 90. But in the data we don't have frequency component for 80 and 90. This one is a kind of aliasing effect, and so that when we try to transform, this one happen. So that in fact we have to discard this last half. We'll see here later some detail around there. Now that is the phase spectrum, the angles. Okay. Okay, here Nyquist criterion. It is important in discrete Fourier transform analysis. Okay, this is a Nyquist criterion. When sampling frequency at frequency f sub x, we can obtain reliable frequency information only for frequencies less than f sub s over 2. Here, reliability means without aliasing problems. So here now, we have here the information, extra information, because of aliasing problem. Okay. Now that is Nyquist criterion. So we can calculate at which value of k, the frequency k delta f is half of f sub s. So from here, if we solve for k, then we recheck this one, and we replace this quantity and that one, and simplify. Then k must be n over 2. So that now only for frequencies less than this one, so that only for k less than this value is reliable, has reliable information, so that in second half is not really reliable. Therefore, we can conclude that the maximum useful frequency f sub max from the DFT output, also it is called the folding frequency, is here f sub s over 2, that is same as n over 2 delta f. In other words, only half of the n available discrete Fourier transform output values are useful. So here case moving from 0 to n over 2 minus 1, because it starts from 0, so that we have to put here minus 1. Okay. Okay, let's see this example. Suppose we sample a signal for t is 4 at a sampling rate of f sub s equal 100 hertz as in the previous example, how many data points are taken? That is now, by multiplying these two quantities, we can get 400 quite easily. How many useful discrete Fourier transform output values are obtained? And that is n of 2. We already know that n of 2, that is 200. What is delta f? Delta f is 1 over capital T. Capital T is 4, so that in each, in the output, the frequency increment is 0.25 hertz. What is the maximum frequency for which the DFT output is useful and reliable? That is now the frequency max is n of 2 times delta f, so that and 50 hertz. That is a maximum frequency that is useful and reliable. The other half of the output values and larger than the folding frequency are thrown out or ignored. So if you try to use it in later analysis, then it produces something wrong, okay, some artifacts. So you have to be careful. But when you try to recover the original signal, then you have to use every the values from the output. Okay. Okay. Now we'll continue in the second part. Thank you.